Hi, this is Dan Bullard, retired electronics engineer, sitting on the front deck of my houseboat again. And today it's snowing. It's really cool. And cool is right. I've got my heater on high, so I'm going to try to stay warm. But it's freaking cold out here. In fact, let me do that. I want to talk about, real quick, the Bullard laws of harmonics, all five. I'm going to try to do all five right now. And I didn't count on the snow coming and being so nice and so wind-free, but we'll see if I can do it. Okay, law one, and here it is on my coffee cup. You can buy this. If you email me or if you contact me, I can give you the graphic and you can order this from Cafe Press. And it's really easy. It's really cool. The first one is, let me read it so I get it right. The harmonic amplitude is proportional to the area of the distortion. That's absolutely true. It's really cool, and here's an example. If I take a half-wave rectified wave, just a half-wave wave, you can see that the harmonics fall off in a pretty interesting way. Notice it's only even harmonics though. So there's one odd harmonic, that's the fundamental. I talked about this in, I think, chapter 1 of distortion. But if you double the area of distortion, that is, if you take that sine wave and do a full wave rectifier thing on it, so you get two humps, then you get the same harmonics minus the fundamental. The fundamental goes away, and where does it go? Now, anybody who knows anything about power supplies knows that you're doing it to get more DC. That's why you're doing it. One more diode gives you more DC. And so what happens is that amplitude in the fundamental goes into the DC, but also all the harmonics double. And so they go up by 6 dB. And so your fundamental goes away, but the energy goes into the DC, and all the harmonics go up by 6 dB. And 6 dB, as I've mentioned in other things, is a factor of 2. And so it's really cool. It's really, really cool. Okay, law 2. The harmonic signature is a result of the angle where the sinusoid impacts the distortion is predicted by the Bullard harmonic solution. I've already done a video that shows you how the Bullard harmonic solution can predict very accurately what the humping pattern looks like. And as I mentioned, there are these idiots out there that think that the humping pattern is due to the sine and cosine functions in the Fourier transform. That's not true at all. Those guys are idiots. Fourier was absolutely right. Fourier was dead nuts on. And so you ignore those people. And here's what, I'm going to show you just a tiny bit of the Bullard harmonic solution. Guess what's in the Bullard harmonic solution? Yes, there's a cosine function. That's where the humps come from. And so the humpiness is from the Bullard harmonic solution, or as I say, the god of harmonics. Okay. I've talked about law 2 a lot, so let's move on. Law 3, even harmonics don't appear in symmetrical distortion because they cancel each other out. Now, law 1 only works if law 2 is there, or I'm sorry, if law 3 is there. If you want to argue with me about law 3, well then you're making law 1 go away. Law 1 is true only because law 3 is true. And so take this example where I have I have a sine wave and I clip the top, and you can see that the distortion looks the same as if you take the same wave and clip the bottom. But if you look at the phases of the two have opposite. The phases of the harmonics are opposite. Therefore, if you clip both the top and bottom, then the phase of one is against the phase of the other. Boom. Those even harmonics cancel out. Okay, law 4 when a portion of a sine wave is removed, I love this cup. I have my coffee in this every morning. When a portion of a sinusoid is removed, such as clipping or almost anything else, then the harmonic signature mirrors the harmonic signature of the feature removed by the sinusoid. Now, I had a guy, Dave Tweed, one of those sites that kicked me off, or they threatened to kick me off, and I left on my own, right? And so he said that, oh, you're not showing the right phase. Well, you can't look at the spectrum and see the phase. So here's an example, really cool. If you remove, and I've done this many times, if you remove the peak, then harmonic signature looks identical. And that's because it is. Now, the reason that you normally don't see that, the reason that nobody else sees that is because generally spectrum analyzers auto-scale. They auto-scale so that you don't get to see it in the same light. You don't get to see it in the same scale, the same range. But if you do it the right way, like I do it, and hold the scale steady with Excel, then I sound like a salesman for Excel, but I'm not. Trust me, I don't. I despise Microsoft. Anyway, that's totally true. The harmonic signature of the thing that you removed matches the harmonic signature of the wave with the thing removed, except that the harmonic signature of the thing that has just the part you removed doesn't have a fundamental, and that's what causes your scale to change. So you have to worry about that. Okay. Finally, Law 5, one of my favorites. It's the last one I discovered. I discovered Law 5 even after I wrote harmonics and distortion. And so Moron Harmonics for Morons contains Law 5. And I finished Moron Harmonics for Morons in like a week. But it turns out that at the end of that, I realized that Law 5 was there. It was true, and I had to talk about it. So I added it to Moron Harmonics for Morons. The phases of the harmonics. Ask anybody, what are the phases of the harmonics of the distorted sine wave? They don't know, they can't even guess, but it's easy. And you know what they are, 4 numbers, 0, 90, 180, and 270. So those are the phases of the harmonics, guaranteed. And the reason for that is really easy, because a distortion in a transfer function always happens in just one place. The sine wave goes up and hits the distortion, then comes down, hits the distortion again, centered around 90 degrees. When it goes down, it hits the distortion near the bottom. If it does hit a distortion near the bottom, it'll hit it again on the way back up. Exactly 270 degrees, that is centered around exactly 270 degrees. So it's guaranteed. So it's amazing. I mean, here's one I did anything and everything I could do to this waveform. And look at all the phases. The phases are always 0, 90, 180, or 270 degrees. Or if you use Daver's law, that's because Daver figured that out. My friend David Reynolds. It's for a cosine wave, it's 0 and 180, and it's really cool. In fact, a lot of people, when you look at information on harmonics and stuff, they'll show you phases of 0 and 180 degrees and nothing else, but they aren't necessarily using a sine or cosine wave. Now, there's some really, really cool things, especially in Law 2. I can back up and talk about Law 2. Is this snowing? A little bit. One of the cool things about Law 2, take a look at this graph. This is really cool. I have a distortion in the waveform, and notice that if you haven't noticed this before in all my other videos, what happens when you see the harmonics in a Bullard plot is you can see that all the harmonics conspire, they line up to create the distortion in question. And so if you look at those, since they're centered around 90 degrees or 270 degrees if it's on the lower peak, then those things, they're centered around 90 or 270 degrees, so the phase has to be, it has to be 0, 90, 180, or 270. Has to be. Can't be anything else. Now, there are cases when that doesn't happen, but then you can use the difference in phase to work out the hysteresis of the device. If there's any difference between those numbers and the values that you get, then that tells you that there's hysteresis. And it's really, really friggin' cool. So I have a lot of videos out there. Please watch them. I appreciate it. I really appreciate you watching my videos. And I don't know why they're cutting me off. I don't know why YouTube is cutting me off. They just let me know that not only have I been demonetized, that was long ago, but they also let me know now that my AdSense account is deactivated. So I can't make any money on videos. So I'm not making any money on these videos, so you can feel good that you're not contributing to my income. My income is, don't worry, I'm doing just fine. I'm doing just fine. In fact, being on Social Security, I'm getting a raise this year. That's great. And so I hope you're getting a raise too. Anyway, the Bullard laws of harmonics, you can get that. Just text me, email me at dan@danbullard.com. It's really tough. Or just comment on the video that you want that graphic, and I'll send you the graphic for that. You can go to Cafe Press, boom. I think I just bought this for my son, and I think I paid don't tell him, he hasn't got it yet, but I paid $15, $16 for this coffee cup. And so it's a great coffee cup. I've already had 2 of them. I broke one, and it's just a graphic. Just paste it on there, tell them to put it on there, and boom, there you go. Anyway, I'm going to go back inside because it's cold out there. But Merry Christmas, and once again, from the river, this is Dan Bullard. See you later.